So, we talked about energy diagrams for a particle with central force acting on it, and for that we have to write the expression of energy. U is half mv square and then potential energy function, but this V can be written as r dot r cap and plus r theta dot theta cap. So, when we use these plane polar coordinates x axis y axis, the position is denoted by this r and this theta, and this is r cap vector, and perpendicular to this in increasing theta direction is theta cap direction, unit vector theta cap, and in terms of these unit vectors velocity is given by these. You can also find expression for acceleration from here. If we differentiate this, you get the acceleration of the particle, the component in r cap direction and component in theta cap direction. If you use this, the acceleration will be r double dot r cap and then plus r dot d r cap dt. Double dot means the second differentiation with respect to time. So, when you differentiate r dot with respect to time, d2 r by dt square is written as r double dot r cap, then keep this r dot here and differentiate this. Here you have three quantities r, theta cap and theta dot. So, differentiate this r dot and keep the rest there, right, and then differentiate this one. So, plus r theta double dot and then theta cap. Now, differentiate this one. So, plus r theta dot and d theta cap theta dt, theta dot. Okay. So, r kept as it is, theta dot kept as it is, and this is differentiated. So, you write this way, and then you know how to write this, you know how to write this. This r cap is cos theta and I cap plus sin theta j cap, because this is x axis. So, this is x direction, this is y direction, this angle is theta. So, this r cap you can decompose in cos theta, sin theta. Theta cap you can decompose as minus sin theta I cap and plus cos theta j cap, and from here you can write what is this dr cap dot dr cap dt. We had done that, dr cap dt. You differentiate this. So, it is minus sin theta I cap plus cos theta j cap. So, this is how it goes, and then theta dot, of course, because you have to differentiate with respect to time. So, this is theta dot and then theta cap. Similarly, you can do this d theta cap dt. If you differentiate this, it is minus cos theta theta dot I cap, and then this will be minus sin theta theta dot j cap. So, this will be minus and theta dot and then r cap, because you have minus cos theta and minus sin theta, and then that minus is taken common, you have cos theta I cap plus sin theta j cap, which is r cap. So, it is this. So, you can put it here, and your expression for acceleration is now, acceleration is r double dot r cap plus r dot and then dr cap dt is theta dot theta cap, theta dot theta cap, then plus r dot theta dot theta cap here, then from here it is plus r theta double dot theta cap, and then you have r theta dot, and d theta cap by dt is minus theta cap. So, this is minus theta dot. So, it is minus theta dot square and then this r cap. So, if we collect r cap at one place, you have r double dot from here and minus r theta dot square from here. So, that is the radial direction, acceleration in radial direction. So, if the particle is here, is moving in some way with some velocity on some path, and you ask what is the acceleration of the particle. So, you can decompose in two components, in r cap direction and in theta cap direction. So, that r cap component will be this, and theta cap component will be from here r theta dot, r dot theta dot, then from here again r dot theta dot, and from here r theta double dot. So, that is the expression. Your radial acceleration is r double dot minus r theta dot square, and the theta component will be 2 r dot theta dot and plus r theta dot. So, you can do your dynamics, two dimensional dynamics in a plane using these plane polar coordinates like this. But at the moment we are concerned with the energy of a particle which is acted upon by a central force. So, you have a center of force and then the particle is here, a mass, and the direction of the force is along this line, radial line, this r cap line, and that is the kind of situation. And for that we are writing our, this is the origin, x axis, y axis, r theta. You can write, if the particle is here, this is r, this is theta. So, energy is half m v square, half m, and for v square we write from here r dot square and plus r square and theta dot square. That is m v square and plus what is the potential energy, v of r. Then we use angular momentum expression to write this r theta dot square, you know, m r square theta dot is L, and from there we wrote this as half m r dot square plus L square by 2 m r square and plus v of r. This whole thing we write as effective potential energy, it is a function of r only, that is half m r dot square and plus v effective, which is a function of r. And it is this v effective r that we plot. So, it is this v effective r that we plot, and this side is r, remember, and r will not be negative. So, everything will be on this side. And what is this v effective r? Here, L square by 2 m r square plus v r. So, if you talk of inverse square attractive force, okay, which occurs at so many places, you know, Coulomb's force is inverse square. If the charges are of unequal type, it is attractive. You can put your origin at one of the particles and the other particle will be doing this kind of central force motion. You have planetary system, sun, earth, sun, Jupiter, and all those things which can be fairly well approximated by this inverse square attractive force. You can have a nucleus and then bombard electrons and see how that electron beam is deflected by this positive nucleus. All those things can be fairly well understood using all this analysis. So, if this V r is minus k r, minus k by r, and this V effective is L square by 2 m r square and minus k by r, then we saw the shape of this will be of this type, of this type. For small values of r, this dominates, it is increasing and positive, and for large values of r this will dominate over this. So, ultimately this will fall faster and the total will be negative, and finally, when r is very large everything is approaching 0. Now, the total energy U, this total energy U I can write on this scale. So, suppose this is the total energy, this is that line, total energy is here. So, you have this particle and this particle has got some velocity at this time, let us say this is the velocity. In this direction it has some magnitude, there is some r here, and at that time it will have some angular momentum L, and the total energy depending on this kinetic energy plus minus k by r. So, initial conditions will tell me how much is the angular momentum L and how much is the total energy U. So, once L is known, then I can draw this, I can have this thing, so I can draw this line, and once energy is known, total energy is known, what is the kinetic energy here, what is the potential energy here, that total energy, then I can draw this line. So, this is the situation. What will happen to this particle further? So, at this time there is some value of r. So, some value of r, suppose this is that value of r, this, remember this is r axis. So, this is that value, initial condition. So, that means on this diagram if I draw a line, this is the potential energy, this is the potential energy, okay, and this is the total energy, this is the total energy, this is the total energy, total mechanical energy. Okay. So, how much is, this is not potential energy, this is effective potential energy, okay, this is effective potential energy, this much. Value of this is given by this point, this much is the effective potential energy. So, one more E, effective potential energy, V effective, V effective is this much. So, if you subtract this effective potential energy from this total energy, so this is the total energy, from this you subtract this energy. So, that means this whole thing from here to here, from here to here, this whole thing is half m r dot square. What remains? Half m r dot square. This is not kinetic energy. Okay, this is not kinetic energy. Kinetic energy is this plus this, but half m r dot square is that full length. Now, what is happening? If this is the diagram, if the particle is going in this direction, the value of r is decreasing. If it is going on that side, the value of r will increasing. So, for this diagram, if I go by this diagram, if I say that no, this is very nicely drawn diagram, it does represent the correct direction of velocity, r is decreasing, that means this point here as time passes will shift here, the r is decreasing. Particle is here, remember this is a graph, this is the particle, particle is going in this direction. So, this length, the separation from origin is decreasing. In this diagram, the particle original r is here and the r is decreasing, means it is going this way. If it is going this way, what is happening? Your effective potential energy is now this much, the magnitude is decreasing, and then the total energy is here to here, this is total energy, and what is from here to here? This is once again, this is half m r dot square. So, value of half m r dot square, which was this much, has decreased to this much. Okay. So, this way things will go, and then somewhere it will go. So, what happens on this diagram? Let us see what happens on this diagram. On this diagram, as r decreases, you are going this side, this side, this side, this side, this side, and finally at some stage r will decrease, at some stage r will decrease, and you will reach here, you will reach here. Suppose r is decreased to this value, and what is this value? If I draw a vertical line here, it just crosses this. Okay. So, at this point, what is the effective potential energy? Here is the curve. So, at this point, this is the effective potential energy, and how much is the total energy? That is always fixed. This is the total energy. How much is half m r dot square? 0. Okay. So, when the particle reaches this point, let me call it r1, and the point, corresponding point on this curve is here, then you have m r dot square equal to 0. So, here for this r1, half m r dot square is 0, so r dot is 0. What does that mean? What does that mean? That means your r is minimum there, dr dt is 0, dr dt is 0, r is a function of time, and dr dt 0 means it can be a maximum or it can be a minimum or point of inflection. So, what is the physical picture here? R is decreasing, 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 decreasing. So, somewhere it has to reach a minimum and then it will increase. So, this particle will go something like this, this. So, there is a minimum R, this is that minimum R. Okay. R is decreasing, 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 and after that it is increasing, increasing, increasing. So, after this point, when this point is reached, the motion will continue and R will start increasing. So, we started from somewhere here. So, on this U diagram, if I point, it is somewhere here, and on this line let me move. R is going this way, that means this point is moving this way, this way, this way, this way, this way, and then this point reaches here, and it cannot go in this side. If it goes this side, then that half m r dot square should be negative, which it is not. So, this is forbidden. This is turning point, not exactly turning point, but in some sense yes, r is decreasing, decreasing, and then start increasing, increasing. So, it is something similar to that turning point. This is the minimum r1, and after that r will start increasing. Your point will go in this side, this side, this side. There is no other turning point. R dot is never 0. R dot is never 0. You go this way, this way, this way, this way. Never you will be intersecting this point. So, r dot is never 0. So, the r dot will keep increasing. So, that kind of path will be there. Similar will be the characteristics if u is 0. If u is not this much, if u is this much, same story, u is this much, same story, u is this much, same story, in the sense that yes, it never reaches here. Okay, if this is u, u is equal to 0, and then your particle goes this side, you have a turning point, so called, and then r is minimum there, and if the initially this particle is not going this way, if it is going this way, r is increasing, then it will keep increasing, right, it will keep increasing, no turning point on this side. But if u is less than 0, if u is less than 0, suppose this is u, then this is the point where r dot is 0, and this is the point where r dot is 0. The total energy and the effective potential energy are same. Here is total energy and here is effective potential energy. So, at the points of intersection, the total energy and the effective potential energy is same, and that means r dot is 0. So, this corresponds to minimum and this corresponds to maximum. If the particle is going towards right on this diagram, that means r is initially increasing, it will increase, 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 but after here it will reach a maximum distance from the origin, and then r will start decreasing. That means on this diagram the representative point will be moving this way, and once it reaches here, again r dot is 0. This time r has reached a minimum, and after that r will start increasing. So, physically if this is the origin, and if this is a circle of radius r, r1, and if this is a circle of radius r2, the particle cannot go inside this circle and cannot go outside this circle. The particle is bound. If u is positive or if u is 0, the path is unbound, it goes to infinity. And in this case where u is less than 0, the particle is bound, it cannot go much away from the center of force. So, for bound paths, u should be, total energy should be negative. What kind of path it is? What kind of path it is? With this much information only, the path can be anything between these two. It can be like this, it can be like this. It is confined in that place, but it can be anything. But if it is potential energy is minus k by r, inverse square attractive, then the things are more definite. We have to do more algebra and equations, but then we can come out with the result. I will just tell you the steps, that the path is an ellipse. Remember, circle is a special case of ellipse. The path, if u is less than 0, the path of the particle under inverse square attractive force is an ellipse. So, it will be something like this, it could be something like this. Minimum separation is r1, minimum separation is r1, and maximum separation is r2, something like this, some kind of ellipse between these two circles. So, that is the path. Kepler's first law states that all planets move around the sun in elliptical paths with sun at one of the foci. So, it is here. Of course, second law we have already discussed, third law will also come if you consider this attractive inverse square law. Now, how to get this orbit? How to get the equation of this orbit? How do I know that it is an ellipse and nothing else? If it is bound, it has to be an ellipse, and if it is unbound, what kind of curve? Okay. So, that also we can I can just tell you the steps the algebra one has to do, or see the textbook and convince that convince yourself that the path is elliptical if the total energy is negative. So, write your energy expression. U is equal to half m r dot square plus L square by 2 m r square and then minus k by r. This is the energy expression, and U and L are known from the initial conditions. Once you know initially where the particle is, you know what is k by r. Once you know what is the initial velocity in which direction and how much is the speed, then you know this quantity, this quantity. So, U and L are defined from the initial conditions, all right, and therefore, you can write this as half m r dot square is equal to U and minus L square by 2 m r square and minus k by r, multiply by 2 by m. So, r dot square is equal to 2 by m and then U minus L square by 2 m r square and minus k by r, and take a square root on both sides. So, r dot is equal to square root of this, and what is r dot? R dot is dr dt. So, dr divided by square root of 2 by m u minus L square by 2 m r square and minus k by r is equal to dt. So, as a physics person, I have done my job. This is now a mathematics, this is a function of r, and here you have dr. So, apply the rules of integrations, this that, to get this expression here. Okay. So, you get this thing r as a function of time. From here you get r as a function of time, some function of time. When you integrate this, you get that. And once you get r as a function of time, you can use this expression that L is equal to m r square theta dot. So, theta dot is equal to L by m r square, and this is d theta dt. So, d theta is equal to L by m r square and then dt, and r you know as a function of time, r you know as a function of time. Once again, it is a matter of integration. You have dt here, you have a function of time. A function of time to be integrated with respect to time, it is calculus matter. So, do it. Once you do it, you get theta as a function of time. All right. So, this is f t, let us call it g t. So, now you have r as a function of time, you have theta as a function of time. You do have initial values of r and theta, you can put t equal to 0 and those values to get any integration constant, and therefore, you know the path point by point. At this time the particle will be here, at this time the particle will be here, at this time the particle will be here, and so on. And if you eliminate time from here and here, you have two equations, r is blah 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 as a function of time, theta is blah 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 another function of time. If you eliminate time from these two equations, what do you get? You will get r as a function of theta, that is path, that is the equation of the path, r is a function of theta. So, this is the way one can calculate and come out with the exact equation that if u is positive, it is a hyperbola. It is a hyperbola. If u is equal to 0, it is a parabola, and if u is less than 0, it is an ellipse. Finish. Remember, circle is a special case of ellipse, and we can work out when it will be circle, but maybe next time. So, under attractive inverse square law, that kind of force, the path of particle has to be either ellipse or parabola or hyperbola, nothing else. And then what exactly it is, that is decided by the total energy, and that is decided by how you start the motion.